let me review the starting point. Well, that's not the starting point. The starting point is the inverse. So that's the best way to think about the logarithm is as the inverse of the exponential function here. So what follows, and that's what we still have to face, is the algebra of the logarithms as it mimics, not mimics, but rather is derived from the algebraic properties of the logarithm. But to begin with, it's just better to think about the logarithm as simply nothing but a function. And what kind of function? It is the inverse of the exponential function of the same base. Okay, so we did that. We flipped the exponential function. So as a sample, one exponential function is on the left over there, and then the corresponding logarithm of the same base roughly is at the bottom. Okay, so as you can see, the x becomes y becomes x, that main becomes a range, the y-intercept at 1 becomes what? Y-intercept becomes the y-intercept of the logarithm, of the exponential function becomes the x-intercept, right? So everything is flipped. So the diagonal is the axis of the symmetry, and so that is why there's such a match between those basic things. But what things does not switch, but rather remains, is the function is still increasing. Right, so it was increasing, it remains increasing, and if you take the different base with an exponential decay function, its inverse will also be decreasing. Fortunately, both of them, once again, they're one-to-one, and so that is why it works out just the same way. Okay, so that is the way to look at all the logarithms at once, and also as functions. Okay, but that's just not sufficient. We gotta actually go down to these greater details of the exponents, and if we want to do any computations with them. And so then we go back to the definition as the inverse, and then write it as an equation. So we have two equations, one in terms of with the same three numbers, and they are just written in two different ways. One with the exponent, and one with the logarithm. Okay, so these are the equation. A is equal to 2 cubed is the same as the logarithm base 2 of 8 is 3. Okay, so just remember that if that is might be hard to remember, but if you remember that it all comes from the inverse functions, then you remember that the base remains the same. So the base of the exponential function on the left, of the logarithm on the right, that's the same number, and then the other two numbers are the input-output, and they are flipped. Okay. So the input is x over there on the left, and y output, and it is converse, the opposite, on the right. Okay, so that helps to understand the logarithm, because you can, whenever you face a logarithm, you can just rewrite it as an exponential function. Okay, so that's what we did below. We took the that pretty much what I have here is pretty much the definition of the logarithm. Apart from if you don't want to think in terms of functions, that's the definition. So log base a of y is to what power I have to raise a to get y. Okay, and then there is a bunch of examples of how it is done. Frequently, it is very transparent. So what is logarithm base 2 of 8 over there? So how do you answer the question? You remember at some point you raise two different powers, and at some point you remember that it was 2, 4, 8, 16, and then okay, so 8 is the power that I need, and so what power it corresponds to, and the answer is 3. Okay, to the third power I raise 2 to get 8. Okay, similarly at some point I did powers of 5. I know that 25 is in fact 5 squared, and that is why the answer is to what power do I raise 5 to get 25? The answer is 2. Okay, finally over there, the power of 1,000, the power of 10 gives me 1,000 because it's 10 cubed. Okay, sometimes it's more complicated whenever you're facing negative, whenever you face division or you face fraction. So that's the last two lines here. So logarithm base 10 of 0.1, you that is, you're going in the opposite direction. So instead of multiplying by 10, looking at powers, so 10, 100, 1,000, you're going backwards and you divide by 10. And so you have 1/10, 100, and so on. And then you know that one division is what it takes, and we know that's negative first power. And as you can see, the logarithm base 10 of 0.1 is negative 1. Which is, incidentally, you can, let me see, as I mentioned, every calculator has that. If you take the scientific calculator, so well, say 100 log is 2. So when log is without the base, that's what that button is. It means base 2 by default. So that's what it has meant all the time. At some point, more logarithms were invented, and so this is called the common logarithm. And then right below is the natural log, and so we'll get to that. But at this time, as you can see, 0.001 log negative 3. Okay, so because it's you divide by 10 3 times in order to get to 1,000. Okay. And then there are fractions, and then there are fractional powers, and which corresponds to, as you remember, to roots. Okay, so in fact, so how do we? You see what's happening? We are trying to represent the question that is put in that box, and so in order to easily answer that question, we have to take that number we are facing and transform it as much as we can into a power of the base. So that's what happened over there in that line. And we start with 0.1. 0.1 is 1/10, and 1/10 means 10 to the first power, and that's how we knew the answer is negative 1. With the next one is we once again try to transform 2 into a power of 4. Okay, so we first write 2 as a square root of 4, and then we remember that the square root is a power of 1/2, and that's why we know that the answer is 1/2. Okay, so that's there's a certain challenge to it, and it is the way I described it, like working your way of that number towards expressing it as a power of the base. That is not a method of any kind of computation. But that's why we have the logarithm, and that allows us to answer some of the questions very easily. Say say 3 is log. Let me write this again. Log base of 8, okay, but or rather, let's go backwards. Log base 8 is equal to 3. What is log base 2 of 5? Okay, log base 2 of 8 is 3 because 2 cubed is equal to 8. So knowing exponents and powers well allows us to sometimes remember or guess or recognize logarithms. That's what that line tells us. What about the second line, the last line here? It is there is no way, or certainly you try to express 5 is 5 a power of 2. Is 5 a power of 2? It's not a power of 2 in the same sense as it's over here. So the answer is no. But it's also a yes. So no, not in the sense as above, because we were able to find it, and we ended up with an integer. In those two lines, we ended up with a negative integer, or even a fraction, or 1/2 over there. So sometimes we simply cannot see what that power is, and that is why the answer is no. But the answer is yes. But the answer is kind of a silly. The answer is log base 2 of 5. So in other words, what's log base 2 of 5? It is log base 2 of 5. Okay, so it is ultimately it's about simplification. So this you can think of this as simplification. Log base 2 of 8 can be simplified into 3. Log base 2 of 5 cannot. That's all. So we just keep it as is because it's not an integer, it's not a fraction, it's some number. What is that number? Log base 2 of 5. Do we have log? I don't think we have log base We don't have log base of anything, unfortunately, but say log, say 100 common log is 2, okay, but if I take, say, 13, and I take a log, what is log base 10 of 13? And the answer is whatever, right? So it is nothing. So either it is an approximation, which is this is, or you just keep it the number the way it is, and log base 2 of 5 is a distant number. So to confirm that this makes sense, to what power there is, I take 2 and raise it to the power of log base 2 of 5, and the answer is 5. Why is it true? Two taken to the power of log base 2 of 5 is 5, because
log base 2 of 5 itself.
Because the functions are inverses. So this one is seen, that kind of a complex expression is seen, in fact, as a composition. So you take 5, then you take log base 2 of it, and then take exponent base 2, and then the answer is 5. And these are the two. These are the inverses of each other, right? So that's why they cancel out. 5 taken to, then applied log base 2 to it, then it is taken to the power of 2, and then, well, not the power of 2, 2 is taken to that power. So we have log function base 2 followed by exponent base 2. They cancel each other. That is why the beginning and the end is the same. 5 is equal to 5. So that's the confirmation or an explanation of what this formula is. It just looks more complex in a way because it's so compact. So if you always, when you have some multi-story building, look at it. So 2, and then there's this whole expression here with log and a superscript and subscript, and then 5 on top of 2. So it's a bit cumbersome, but you can always break it into compositions. If you just one way to do it is just to see that you have parentheses. So 5 is what is 5 is the input of the logarithm, okay, and then this. The whole logarithm is the input of the exponential function. So you read it as always we do from inside out, and if you have parentheses placed judiciously, then you know in what order things are happening. 5 logarithm exponential base 2. Okay. So that's how it works out, and based entirely on our understanding of the logarithm as the inverse of the exponential function. So naturally, you can rearrange the terms in the opposite order, and it will have the same effect. So I'll take that row here and flip it around. So I'll put it take exponential base 2, and here I have take log base 2. Okay, so if I start with, say, 7, I will end up with 7 because of the same reason, because these two functions are inverses of each other, okay? But this time, what that understanding of two compositions written separately, I want to take it backwards to algebra. So, so these are diagrams of compositions, okay? And then the algebraic representation is more compact. This is algebra. And we need to know both. And so, well, this is the algebra for the second line. It is what? So I start with 7 and start to build up from inside out. 7, then I apply exponential function base 2. So it will be, what, 7? Starting point. Starting point is 7. Then what? Take exponent base 2. So what do I write here? No, not log, just power base 2, like this. right? So that's the first step. This is the step that we're taking, starting with 7, then take exponent base 2 of this function. So 7 is the input of that function, okay? And so that's the first stage. And the second stage is now this, what we're looking at is now the input of the next function, okay? And so we just write it out. And once again, we're unfortunately moving from right to left, a log base 2. And the answer is 7. Okay? So once again, the algebra, most of the time you see nothing but algebra. So you remember that behind that algebra is a sequence of compositions that you can write out in a more spread out, but ultimately easier to understand way as such a like a flowchart way. Okay. So that is the most basic thing about logarithms. The time, something we don't have time for is the exponential models. So I'll just let me quickly outline them in addition to what we have seen already. So there will be, well, let's the simplest one as we have seen. So you have $1,000 and you have 1%, well, let's say 10% APR, and then the direct question about this direct problem about this exponential model is how much I will have after 10 years. Okay, so the answer is naturally it will be 1,000 multiplied by 1.1 to the 10th power. Okay. So in other words, compounded interest. Now the inverse problem for the same setup. The question is how long, not how much, how long will it take to reach, say, 2,000? The answer is that will involve the logarithm. So you can see how we reverse the problem from left to right. So in the model, the model is let me write. The model is 1,000 times 1.1x. Okay, so let's say f of x is that's the amount of money you've got on your account after x years is 1,000 times 1.1 to the x power. Okay. Now we reverse or inverse it because now x is our interest. We do not plug in x into our formula, which is what happened in that column. We instead x is what we're trying to find. So what's the answer is the short answer, solve the equation. 1,000 times 1.1x is equal to 2,000. That's the short answer. The actual answer is well, you can tell me it is what? Well, let's just solve it. 1.1x is equal to 2. X is equal to what? Look at it. To what power do I raise x to get 2? To get 1.1 to get 2. That's what x is. So it's also known as the logarithm. So x is log what base? There are two numbers left, 1.1 and 2. Which one is the base? No, the base is the base on which the exponential function is residing. X is the exponent. It's on top of the base. Okay, so 1.1 is the base. 1.1 of 2. That's the answer. Okay, so like it's always with inverse problems, you end up with solving an equation, and you solve that equation with the newly discovered function logarithm. Okay. So that's model 1. Model 2 would be, say, population growth. So you have 1 million people, and you have decline. Well, let's say decline loses 5% of population. Then after X years, you have 1 million times 0.95 power of X. So you multiply, every year we multiply by 0.95, even though with this formula, that previous development helps us also to answer the question not only what happens after exact number of years, it will tell us what's going to happen after 8.5 years, for example. You just plug in X equal to 8.5. So that could be the question: how low is the population after 8.5 years? And it does not have to be a number that is an integer, but it will be, once again, 1 million multiplied by 0.95, 8.5. So all of this can be, incidentally, can be computed with a calculator. Here it is. There are buttons if you never use it. There is a button on the right, x to the power of y. So if I need to see 0.95 to 8.5, 0.95, I believe 8.5. Okay. Look at this, at the little letters at the bottom, top right. 0.95 to the power of 0.85. Okay, and so as you can see, the population will be 686,000 after 8.5 years. Okay. And then, so that's one model which is common, obviously. If you model any kind of population that grows proportionally to its size, which is a natural assumption, by the way. Compounded interest is naturally every dollar brings you as many cents as the next one. That's why it grows proportionally. The population grows proportionally because roughly there is a particular birth rate or maybe decline. It is once again proportional to the population because the likelihood of a person to die is roughly the same, and so that's why if roughly speaking, out of 100, one is likely to die per year. Then if you have 1 million, then you'll have 1,000 die, right? Or if you have 10,000. Okay, so that's the proportionality idea that why it works out. Now the inverse problem is once again the question will be instead of how much or how little, the question will be how long or when. Well, let's put it differently. So when will the population reach, say, 500,000? And the answer, once again, solve our equation with the equation on the right. So we have 0.95 to the power of x is equal to 500, or 0.5. So if we're doing everything in the millions, that's what it is. And so the solution is, we know once again, to what power there is 0.95 to get 0.5. And the answer is a logarithm. X is log. Base comes from the base. That's the base of the exponential function. That is why over here the base ends up to be the base of the logarithm. Okay. So then this is 0.95 is the base, and it is equal of, and now the other number becomes the input, 0.5. So it was output here. Output of the exponential function becomes the input of the logarithm. So since the calculator does not have base, chosen base, it only has logarithm of natural log and base 10 log. So I cannot do anything with that. So that is, but one of the reasons is use, which is we're not ready to ln natural log or to compute everything, because one can be converted into the other, and that's still to be discussed. But at least we know that we can do that if we want to, because if we have the exponential function available, and we do. In fact, I could do trial and error to find out roughly about how long it will take to reach 0.5. I already know that it's going to be what I already know that. After 8.5 years, the population has reached 6.4, so I need to wait a little bit more, maybe 10 years. Okay, so 0.95, power of 10, maybe. Sounds reasonable? Yeah, so still not dropping, so maybe try 11 years. So 0.95 to the 11 after 11 years, 5, 6. So actually, it starts to decline slower and slower. So maybe 13. One more time. 0.95 power 13. Okay. So roughly a little bit more than 13 years it will take for each to reach half of the population. Takes a while. And so these are two main models. There's the third one is radioactive decay. So the situation might be, say, carbon-14 or whatever that is, lost half of its mass after 5,000 years. Okay? So, and then we want to know, for example, a bunch of questions we can ask about how much it still has after 10,000 years. How much after 10,000 years? It might matter because so it's been 10,000 years. You want to know, is it safe to go there? Okay, so what's the answer? So this radioactive element loses half of its mass every 5,000 years. How much does it lose after 10,000? The answer is not 0, by the way. You will not be left with 0, so that's a common mistake.
Would it be 1/4?
Yes. The answer is 1/4 because you multiply by 1/2 twice, right? So 1/2 times 1/2 is equal to 1/4. You certainly can, and it is a power just applied twice. So it's 1/2 taken to the second power. And that's the answer. But then there is the inverse problem, and that will be once again when. When is it? When does it lose? Say 90%. Maybe the standard is that it has to lose 90% of its mass in order to be safe. So you want to predict when it's going to happen, and then that's the inverse problem. And we already know, once again, we got to solve 1/2 power of x is equal to 0.1. So we're left with 0.1, right? And so how many times do we have to take multiply by 1/2 in order to reach 0.1? And the answer is, we already know, once again, not trying to actually solve the problem by trial and error. We have the answer. The answer is logarithm. Logarithm, what base? What? Half. Okay. Of 0.1. Okay. So once again, you can try to once again this needs more work. If we want to actually solve the problem, if we take the problem as stated and we want to solve it and we want specific numbers rather than just logarithm, you need a calculator. This, even though it's called scientific calculator, does not have a logarithm of any base that we choose. So we're going to need a conversion formula for different bases. But we can do trial and error just to see how long it will take. So You want to guess how long it will take to reach 1/10? How many times do you have to multiply by 1/2 in order to reach 0.1? I don't know. I would try 10 to begin with. Hold on a second. Yeah, 0.5 power 5. Okay. Okay, so that's a bit more. So it will take less than that. So again, 0.5 taken to the power of 2.5 maybe. Not enough. So is it? So 3 is too much. Well, 3 is close, so it's just about 3. So in other words, it will take 3 of what? 5,000 times 3. So it will take 15,000 years in order to the amount and the danger of this radioactive element to reach 10%. So imagine that if it requires 1%, then well, that will be taking even longer than that. Another interesting application of the same thing is as you may have heard, carbon dating. Anybody knows what that is? Carbon dating? Yeah, so the same idea, only you look backwards. So you're looking at how much of that carbon is left in the painting, for example, and you compare it to how much it's supposed to have when the tree is cut. So the paint is made from plant material, so the tree was cut, and then it starts to decline exponentially. Okay, and then you ask yourself backwards. So if it right now it has half of the material left, it means that half of the material of the carbon is left. It means that the tree was cut at least 5,000 years ago. Okay, so if it is more, then it is more. Okay, so that's how they date all of those moments. 5,000 years, but it doesn't have to be this long. If any painting, 100 years, 200, it still works. And it's based on the exponential decay. So the first two compounded interest exponential growth. Population could be growth or decay, either way. And the last one is exponential decay. Okay. Okay, so that's just to be familiar with why we study exponential function, and the logarithm is here now. Okay, so that's all good. This is why, but really what we have to do is we have to match the algebra that we know about the logarithm, about the exponential function, with that for the logarithm. So these are the 3 main properties of the exponential exponential function that we know, that allows it to do computations without calculator whenever necessary, and that's what we are gonna do now with the logarithm. Okay, so let me take the first one. So ax ay is equal to ax plus 1. So that's the basic property of the exponential of the exponent. Really, nothing really necessarily have anything to do with functions. That's just the property of the exponent. Remember, in case you don't remember this is where it comes from. Always good idea to remember. X times y times all together x plus 1 y times. Okay, so now, what does it tell us? About the logarithm? Well, the answer is try to find the answer. Try to eliminate the exponent, and that's how it's going to be. We eliminate the exponent from the formula, By using what we know about the exponential function. So it is the inverse. So let me write the definition, also known as the cancellation property, or two of them. So one cancels the other. So number one, remember we just talked about a log base A of x, let me put capital X here, is equal to x. With one cancellation, and the other one is in the opposite order, a log base A of AY is equal to 1. So these are the two cancellation properties. So we're going to use them. Trying to eliminate exponent from this formula. Just remember, these properties are nothing but the definition. The definition of the inverse tells us that the two functions cancel each other no matter in what order that we put them, and that's why we have two properties. Okay, so one way to eliminate the exponential function is the most direct. It is just apply log base A to both sides. Remember, that's one of those methods of solving equations is exactly that. If you want to get rid of a function which isolated on one of the sides of the equation, such as exponential function is isolated here, you can get rid of it by applying its inverse. Okay, and then the second thing that we keep in mind every time we solve the equation is that two things are equal to each other. You apply function, the result will still be two things equal to each other. That's the nature of a function. Same input, same output. So if we look at that equation as the equation, equality of two inputs, then we're going to two outputs also equal to each other. So that's what I'm talking about. AX, AY equal to AX plus Y. Now let me put it here. AX plus Y. And now I do what I say here, apply log to both sides. So this is what I do like this. Log base A. Log base A. And then as promised, we have cancellation. Over here, this is the cancellation. So I am invoking this property over here, the second cancellation property. So it means that x plus y will drop out, and it will be simply equal to x plus y. Okay. Unfortunately, and that's you have to be careful about that. There's nothing like that will going to happen on the left. On the left, there is no a is not the exponential function is not isolated. Therefore, it cannot cancel. Cannot be canceled by the logarithm. Okay, which means that we still end up with this kind of a complex equation of a mixture of the logarithm and the exponential function. So on the right is very nice and simple. On the left, we have two both logarithm and the exponential function. So how do we get rid of this is what needs to be get rid of. So how? This time we substitute. So apply log to both sides, substitute. And what I mean by substitute is say x is equal to log base A of x capital, and y is log base A of y capital. So the idea is the same. If I plug in these functions, they will cancel those exponential functions very easily. So I have log base A to what power? It is log base A of x capital, and the second one is A log base A of y capital. And on the right, I have the sum of these, log base A of x plus log base A of y. Okay, so it looks for a moment complicated, but not until we cancel things out. And these are, once again, we have two cancellations. Well, those come from the first cancellation property. So these are literally disappear, just like we were able to eliminate this one. These disappear, and we have a new formula. So a log base a of x capital is x capital. So this whole thing is x capital. This whole thing is y capital. So we end up with log base a x times y is equal to log base a of x plus log base a of y. Okay, so that's the property 1, or rule 1, of logarithms. So let me write it next to, or let me copy my property where it came from, this property where it came from, the property of the logarithm, and let's put them side by side and see if there is any match or some kind of a analogy. Ax, ay is equal to ax plus y. Okay, so we're not referring to the same x and y, as you remember. So, but this is where it came from. So from the formula at the bottom, the new formula comes from. So multiplication is still recognizable. The signs are the same. These are the same signs. So a multiplication on the right, multiplication on the left, addition on the right are still the same. It's what has happened to the rest of them looks different. Okay, so then let me see what if anything it might help us to compute log base log base 2 of say 1/4 times 8 can be broken apart. Log base 2 of 1/4 plus log base 2 of 8, and then this one is log base 2 of 2 negative 2 plus log base 2 of 2 cubed, and then it's negative 2 plus 3 is equal to 1. Not surprising, because this log on the left is simply 2. So the answer is 1, just to confirm that the formula makes sense. But really so there will be 2 more properties, and well, let me write the second one here. Log base x y is equal to y log ax. So I'm just writing it here because we are short on time, so deriving that property can be derived, that's rule number 2, can be derived in just take a little bit of time to derive it from the properties of the exponential functions. So this one is especially convenient, and so we'll discuss that. But the one on the left is, even though it's not as maybe as noticeable as we're going to see as the second one, it is in fact very important historically, because look at what happened here is we have multiplication on the left and we have addition on the right. So it is a conversion of one operation to the other. So that's how they carried out before the calculators or computers. That's how they did multiplication. Have you heard of it? Right? So when you need to multiply 2 large numbers, that's the way they did it. To multiply 2 large numbers, and naturally it is very hard to do, because you remember how you multiply. You have to. It's a long computation. So what you do, and you need an approximation. So instead, what do? You take the logarithm of the first number, logarithm of the second number, with those big tables of logarithms, and then add the results together, giving me the right-hand side. And then how do I find x to y? I take the exponent. Okay, in other words, this is the plan. So x, from x to log base, they usually use log 10, I think, x, and y is replaced with log base 10 of y. Okay, then add them together. Add them. Okay, and then apply exponent base 10. And that will be the same. The result is x times y. So as you can see, we have avoided multiplication altogether. It seems like a roundabout way, but actually, if you pre-compute all the logarithm ahead of time, it's not so hard because the answers are right there, and then the actual operation that you have to carry out by hand is this one, addition, instead of that one, multiplication. It's just how it happened. It is really how it happened, and that's how they work. Okay, so rule number 2. Rule number 2 is actually sort of familiar. If you just think about, if you take the special case, take x equal a. If you take x equal a, you have log base a of a to the power of y is equal to y times log a of a. Okay, what's log a over a? It's 1. To what power do I raise a to get a? The answer is 1. Okay, so it is, in fact, y times 1, or in other words, it's y. Okay, so then if we look at what we're left with is really not anything new. This is familiar. It is simply cancellation property again. So the cancellation property that we just talked about, log base a, applied after the exponential function base a, and they cancel each other out, and we have y. So that formula is just more general formula than that, and it is derived from this one, ax y is equal to ax times y. Two consecutive applications of the exponential function. Okay, so I think I'll stop here and we'll just continue next time. We've got to wrap this up. We still have a couple of topics for next week to address before the final.